applications, and this is a bunch of material not in the book. With respect to the class, you'll be expected to know the generalities about these applications, how SVD is applied, but not necessarily solve the equations that go with them. So for now, we're going to assume that you remember SVD when decompose A into three matrices: the left singular vectors, the actual singular value matrix, and the right singular vector is V. Just think of them now as a black box. The code for that is widely available. I don't actually recommend you ever implement it unless you become a numerical analyst yourself. For example, in MATLAB, you call by simply having square bracket UVW, square bracket equals SVD of A and 0, and it'll go off and compute it. And there's lots of other libraries for different languages. So the WI are the singular values of A. A is singular if some of the WIs along the diagonal are 0. In general, the rank of A will be the number of non-zero WIs. So if the matrix is non-square, that's especially important. And the SVD is mostly unique. It's actually unique up to a permutation of singular values if some of the WIs are all equal. So if I have 3 equal eigenvalues for A transpose A, then I will have 3 equal singular values. And then you can rearrange the columns, but it will still be unique. So now we want to really look at why is it so useful. So the first of these is an application of what we call pseudo-inverses. So if we just think about a pure inverse for a second, if I wanted to compute A inverse and I have the SVD decomposition, well, I could simply take W transpose inverse, W inverse, U inverse. But since U and V are orthogonal, their transpose and their inverse are the same thing. So we just get V, W inverse, U transpose. Just using the fact that the transposes of orthogonal matrices are their inverse. And since W is diagonal, we already know how to take the inverse of diagonal matrix really easy. You just take 1 over the entries that are in it. So therefore, I can write the inverse very easily. The problem with that is it fails when some of the WIs are 0. It's supposed to fail. The matrix is singular. We can't expect there to be an inverse for a singular matrix. And here's the really strange and clever part at the same time. When we're trying to take the inverse of W, if I have a very, very small number, so it's not exactly 0, it's 10 to the minus 30, then when I invert it, it's going to become a very big number. But if I look at the way the singular value decomposition works, if I replace WI, instead of, when WI is 0, or actually if it's very small, instead of setting 1 over WI to infinity, we're going to set it to 0. So because we can't do this stuff with infinity. So whatever the number, instead of making it really big, we're going to set it equal to 0. And it turns out that this will give us the closest matrix to the inverse in terms of the Frobenius norm. But it's the closest matrix we can get. Just like when we have our over-constrained system last week, we talked about how you can do least squares. Well, it turns out pseudo-inverse is really the same kind of thing. This idea of a pseudo-inverse is defined for all matrices. It doesn't matter if they're non-square, if they're singular, or whatever. There's always a pseudo-inverse. And if the matrix, if ATA is A transpose A is invertible, then A transpose A inverse A transpose is actually equal to the pseudo-inverse. And that just follows because if we take this and put these back in the singular value decomposition, you'll see as we write it out, all kinds of things cancel out because of the properties of orthogonal matrices. So this then gives us a nice clean way of doing the calculation of the pseudo-inverse. So let's let M be our product of our SVD decomposition. So M is our matrix now instead of A. If we multiply to see where this goes, if we multiply by both sides by the inverse, we'd get 1 for the left-hand side. On the right-hand side, we'd get M inverse U V W transpose. If we now multiply by V, we're going to get V, because V times the identity matrix is V. And on the right-hand side, because we post-multiplied V transpose V is the identity, so it's going to go away. Multiply now by W inverse, and we see, again, we get V W inverse, and W inverse times W is W. It goes away as the identity, and so on. So as we go through this, we just get this. Now we have to be a little careful when we're doing that. We can't just take W inverse again, so we're going to use this pseudo inverse of the diagonal that if the number is very small, then we're going to, in absolute value, we're going to set the diagonal element to 0, and we get this back to our pseudo-inverse. So now let's look at solving a set of equations with that. So if I have capital Mx equals b, I really have two cases. If b is equal to 0, the right-hand side is 0, then x is known as the null space, which we've already talked about. And now we have to find a way to solve that. Well, it turns out if I have the SVD decomposition, any column in VT associated with a singular value in W that is 0 gives us the elements of the null space. In fact, the total null space is the set of all vectors in VT associated with singular values in W. So we already directly get the null space. It's pretty easy. Now, if B is not equal to 0, well, then we're going to take its SVD decomposition. We're going to take the pseudo-inverse, and then we can solve this by just taking the pseudo-inverse times B. So I take B times U transpose W inverse and V. That gives us the way we're going to solve it. So it turns out that solving AX equals B in a least square sense is exactly doing this equivalent computationally to the pseudo-inverse of A times B. So this gives us another way of solving least squares problems. It has the advantage that instead of just trying to solve it, it also lets you see if your data is singular. And even if your data is not singular, and this is important, we'll talk about what's called the condition number at the end of the lecture, but the ratio of min to max singular values tells you something about how stable your solution will be. And in general, if you're working on a modern computer, if the ratio of the maxes to min singular value is greater than 10 to the 8th, you have a problem with single precision numbers. If it's greater than 10 to the 20th, you can't compute stuff even with the double precision numbers. And so if you look at that ratio then and it's bad, so not exactly 0, you still want to set very small ones to 0, which will give you a better least squares solution. So want to look at this sort of graphically, talking about the rank and the range and null space, make sure you get all this from the matrix. So if I have some matrix and I do its decomposition, and so in this case I'm going to show you all the middle matrix W. It's got 3 proper singular values that are greater than 0 and then one that's 0 and doesn't, in this case I actually drew it with an extra column. So what happens? Well, our rank is 3 because we have 3 singular values. The range of A, the space that is the normal space, is the 3 columns of U associated. So the first 3 singular values are non-zero. The first 3 columns give me the range of A, and the null space are the 2 rightmost columns of V. Okay, so last part of the lecture, we talked about how we can view all this as a rotation. And so how is it that this is both simultaneously sort of transformation and rotation and all of this? Well, it turns out that that's the part of the unique properties of that. The null space defines part of what that rotation has to be because it's actually then part of that is dealing with the projection for the null space elements. Okay, so from the SVD, if I give that to you, you should be able to look and say, here's the range of a matrix, here's the rank of a matrix, here's its null space, and then use it. So now let's look at how we can use this to solve some real problems. So let's go to a data fitting problem. I'm actually going to do it first with this example here, which is nonlinear. Then we can do it with a linear example based on what was in the book. So if we have y equals ax squared plus bx plus c, if that's our model, so we're looking at something that might be accelerating or the angles of things as we're sort of drilling in this example here. Think about how much pressure is going on. We have some quadratic model. So we build our coefficient model matrix, and we have 1, x1 squared, where x is the location I've evaluated it. So each data point here is at some value of x, I get some value of y. So here's the value of x, here's the value of y, but we build our matrix S by taking the square value in 1. And that'll then give us we solve this in least square sense. We're going to get our 3 coefficients A, B, and C that fit this equation. Well, how do we do that? Well, in MATLAB, assuming I've done the SVD decomposition, I simply take U transpose Y, where Y is our right-hand side, times V inverse, 1 over the diagonal of the elements, times V, and that is our solution. If you look at this, you'll see, of course, that is just the pseudo-inverse written down as a sequence of steps. And although here it looks like a formula, that's other than the dot being a times and the transpose being a quote, you could do that directly in MATLAB. So just put this in numeric examples. Let's revisit the temperature time thing we did for the best line fit in the previous chapter, and sort of relate this back to, we'll see what SVD and how it was related to the A transpose A Gauss matrix we developed before. So here we have our model, which is x and 1. So we have some temperature at some time, time, and times this gives us our temperatures. Go to fit our data. So if we go to compute the SVD of this, you're going to get 3 matrices. Your diagonal matrix, or sigma in this case, has 2 singular values, 95.25 and 0.17. You can take its pseudo-inverse and you get 0.01 and 0.68. U and V, I'm not going to show you here. I think they're actually in the book. And then to solve it, we simply take U transpose times B. Okay. And then we take the pseudo-inverse times that, and we get 2 numbers. Then we take those 2 numbers and we multiply them by V, and we'll get the best fit line. And if you follow through this, and again, there's a little bit more detail in the book, you'll see we get exactly the solution that we got by doing least squares in the traditional sense. Okay. So there's a bunch of other applications. So another application has to do with image processing and denoising. So if I actually were to take a matrix, and again, we've already talked about how to represent an image as a matrix. So if I were to take SVD of this image, make it one big column matrix, and then take the SVD of that, and I get the singular value decomposition UVW, if I look at the first singular vector of that matrix, I'm going to get and I take this product. So I'm going to take V, right, colon, comma, 1, transpose. So that's the first column of V times W, the first element of W times U, and I take that product, right? This is 1 by n, this is n by 1, this is n by 1, and I multiply all that, I'm going to get an n by n matrix, the size of my original image. So A was n by m, this is m by m, this is m by n, and this is n by n. So I'm going to multiply these back out, I get an n by n matrix. And interestingly, you can sort of see here, the first of these reconstructions actually captured a lot of the structure that was in this image. These vertical bars that are between the magic squares and the edge of the image are captured by this representation. The first bit of this has a lot of interesting information. And although I'm not showing it here, you can do this for denoising, where you might, for example, take the first 10 coefficients and reconstruct it. And if that sounds a lot like what we were trying to do with faces, it's actually very much related, because these are eigenvectors of A transpose A and A transpose, and so there's a strong relationship between what we're doing for image reconstruction. So to do this as a method of signal processing, we do the SVD decomposition, and then we look for small singular values of A. So instead of saying 10 to the minus 20, we might just say anything less than 0.01, and then reconstruct the image. And it turns out that by doing that, I can get rid of a lot of noise that was in the image, because noise turns out to be higher frequencies, which doesn't show up in that information. Okay, related to that is image compression, where if you want to find the best rank K approximation to A, you set all but the largest K singular values to 0, and you multiply that back out, and you're going to get a very compact representation. If you do this by eliminating the extra columns of U and V corresponding to the zeros, so if A was originally a very large matrix, and I get rid of large amounts of it by doing this low rank decomposition, I'm going to keep 2 or 3 columns of U, which may be big, and 2 or 3 columns of V, which aren't going to be very big at all, but this is still way smaller than the original matrix. So you can use it as a kind of image compression in a least square sense. Okay. So there's something else we can do with it, again from a computer vision point of view, just to show you a couple other examples. If we're talking about structure for motion, or SFM, on our orthographic projection. So now let me think about what happens if I'm looking at a point in the scene and I'm projecting it into the world. Well, when I take a scene point and I project it through a projection matrix into an image point, I can view that as a transformation, a linear transformation. And even with the image offset, I can view all of this. And we've already looked at how to do those transformations. But now it's sort of interesting. Can I actually try and recover from, say, a moving camera, the structure of the 3D world, assuming the world is sort of rigid. So as you drive by a building and look at it, you get the ability to answer these kinds of questions. So part of our trick is to choose the scene to be the center of the 3D, choose the image origin to be the center, and then the math drops a little bit out. That allows us to drop the camera translation. So I'm just going to do that to make this a lot easier to go through this simple example. So if we do that, then we can see that for a set of points, so if I have a bunch of points on a model, and I project them into U, I'm going to get U1, right? Our U is our 2 by 1, 2 dimensions by 1, and if I do a vector of them, it'll be by n. Is a product of a 2 by 3 matrix and a 3 by 1 set of points. So if I do any of those, I get this large matrix of data. And the interesting part, and an observation made by TOMASI and KANADE in 1990 in their paper published in 92, was that the measurements that I see in the world, so if I watch this same point over a sequence of frames, so I see where it is in the first image, and the second image, and the third image, and as I do all of that, those are my measurements for its location in each of the images for each of n points. So I get 2f times n, I get 2f because I actually have its x and y location in each of those two frames. That matrix has to be representable as a product of the motions, which is just the separate projections for each of the cameras, times the shape, and the shape doesn't change. Okay, so the key observation of this is then that the rank of W, even though it's a big matrix, has got to be less than or equal to 3. If there's only one motion in the scene, because there's only one of these, then it's a product of a 3 by n matrix, which has rank at most 3, times 2f by 3 matrix, which has rank at most 3. So the product of these two rank 3 matrices has to be rank 3, giving us our measurement matrix. So now we can be clever and say, oh look, well if it works that way, now if we consider W to be known, we want to solve for M and S, we can look at this, looking at this in terms of the singular value decomposition, and say what we want to do is basically break it up. So if we think about the singular value decomposition, S is related to the right singular vectors, M is related to the left singular vectors, and what we really need to do is solve for A. We're going to introduce this little A in the middle, is solve for A by enforcing metric constraints, and this will actually give us a way of looking at what would be our singular value decomposition. So through the SVD, we can now try and solve this problem. Even if we had noise, it turns out that we're going to try and solve this with the optimal rank 3 approximation, because our goal is to ignore the noise, and so we do pretty much the same thing. We estimate the W prime, the noise-free factorization, and then we go ahead and compute this between the images. There's actually lots of extensions for this idea of structure for motion to deal with independently moving objects, perspective projections, outliers, subspaces, and a bunch of other elements. And just as an example, I did a paper back in '91 where we actually showed that if I have multiple moving objects, we can actually use the SVD decomposition to decompose them, because if I look at this right singular vector, over time they form little clusters as the points move through space. The right singular vectors and the coefficients of them are only slightly changing, and so if I have multiple motions, in this case I have clusters for 4 different motions going on in the scene, because all the motions clustered together. And so not only can we use them to factor the motion, we can actually even use it to estimate the data. So lots of other vision applications use SVD, because there's lots of stuff where we represent it in a linear system. So we've talked a lot about least squares. In fact, part of this factorization is related to least squares. But now I want to come back to a slightly different kind of least squares called total least squares. In our first interfaces with least squares, we were looking at things, and actually we were thinking of it as sort of y equals mx plus b form. We were doing least squares in a vertical sense. So our errors were always measured assuming the point didn't have any error, just the vertical measurement did. But in reality, we often have coupled measurement errors. So in fact, if I try and measure at a particular time, I might be a little early, I might be a little late. If I try to measure a particular location, I might get a little off. And so rather than measuring by assuming x is perfect and y has all the error, a better solution is to do what's called total least squares. And what you really want to do is find the line or the linear structure that it best fits your data where error is going to be measured perpendicular. So we're going to go through this just to derive it, and you'll sort of see how it ties into SVD in a minute. So to solve this problem, if we want to think of the distance of a point to a line or a point to a plane, we're just going to take the coefficients, dot the normal minus our constant. where A is the normal to the line or the plane or anything else we're trying to minimize, look at. And here's how we derive least squares, and you'll see where we get to this. So we take our point, now we have our distance, and all I want to do is now minimize the sum of the squares of those distance, hence least squares. I want to find the coefficients that are going to let me solve this and have the minimum error. Now, if we pretend we know the solution for n, we can then use it to solve for a. So for a second, let's just pretend we know the normal. Then the a, the free parameter of the other free parameter plane, is just given by x, y, or larger and higher dimensions, dotted with n, summed over, and take the average. So that lets us say that the offset is just the average from this dot product. And if we do that, then we know that our distance, we can plug this back into our distance and get that our distance is just x sub I minus the sum over x sub I, the mean, and y sub I minus y sub I over m, or its mean, dot n. Okay, so far what we've done is just assume we knew one, we'll plug it in, so we get it back into an equation with just one set of unknowns, n. So our goal is then to minimize this mean value. So if I let that go in, because this is really just x minus its mean, that's just a different value, transformed, right? We subtract off the mean value, and now our goal is to minimize xi and yi dot n squared and sum all that up. Now, if we want to do that, we're going to use the factor from calculus that the minimum occurs where we take the derivative. So we can take the derivative and set equal to 0. We write this down as a linear system, xy times nx ny equals 0, and put them all together. Give a large matrix. Notice this matrix is not square. And we then want to solve an equals 0. This, of course, has some problems. There's lots of solutions, including n equals 0. Least fat, in fact, if we do very standard least squares, we'll just get n equals 0 as our solution. So we have to find a better way of getting the solution. So we're going to do that by using SVD. But first, let's get to sort of one of the places this will often happen. This idea of getting 0 for the least square solution occurs not just when you have total least squares. It'll occur also when you have under-constrained least squares. So if I have fewer data points than my parameters, you can't do standard least squares. If you recall, the standard solution for least squares was to take A transpose A times X equals A transpose times B. But when A has more columns than it has rows, A transpose A is singular. You can't take its inverse. So we're going to have a problem with that. So the solution we're going to look at will address this as well. It'll in fact address one more even subtle problem. What happens if you have more data points than unknowns, but the data actually just poorly constrains the function? So let's go back to the quadratic we looked at and say I wanted to fit ax squared plus bx plus c. Well, if I had a lot of data along the quadratic, it worked pretty well. But if these are my data points, it turns out that there's a ton of lines that go pretty much through them and that don't have much difference in their error. So it's very unstable. So even though I can formally solve this one, it's under-constrained in a more logical sense, and it's going to be extremely noisy. So it turns out all three of these problems are very related. If the problem is very close to singular, the round-off error is going to have this huge effect. So we can detect this in lots of different ways. In our least squares matrix, the uncertainty of our covariance, if we're looking at it from a covariance point of view, is going to be related to small values in the singular values for A transpose A. And the reason that happens is because if I take the product of X transpose AX for any small x, it can be problematic. It'll be moved to a different location. So going back to singular value solutions, part of our idea was anytime you get something that's close to 0 being unstable, just set the associated singular value to 0 and avoid corruption of the good parts. So that brings us back to this idea of what we call constrained optimization, which is how we solve our total least squares problem as well. So if I want to solve this, I'm going to put in a constraint in this case. So I'm going to try and minimize an squared subject to the norm of n equals 1. So instead of just saying any solution, we want to write this down where I'm going to try and find of all the solutions, because we know there's infinitely many, find the solution whose norm is closest to equal to 1. Well, if I do that and I look at the norm of A times our answer squared, I'm going to get AN transpose AN. That's just how I compute the square distance. That's N transpose AN. If I expand that in terms of the eigenvectors of A transpose A, I'm going to get that the norm is just equal to, if in the 2D case, the square of the eigenvalues, where lambda I is the eigenvalue, and we get this elements for these two. So if I really want to minimize that, now what I need to do is minimize that subject to mu1 and mu2 equals 1. And you can do that in lots of ways, but the easiest way is to set one of them equal to 1 and all the others equal to 0, which is to say that n are normal to this solution of least squares when we have these degenerate problems, is the eigenvector of A transpose A with the smallest corresponding eigenvalue. So, do you think you know how to solve that? Think back to when we showed you what U, V, and W are. Okay, so now we want to look at another example problem where we're going to apply SVD. We're going to look at production models in economics, and actually we're going to use this as a simple example of a broader class of equilibrium problems. But imagine we're trying to consider in a closed economy something that has one steel plant and one coal mine. And the two are related. I take steel to run the mine, it takes coal to make steel. So to produce 1 ton of steel, assume it takes half a ton of coal consumed by the steel plant. To produce 1 ton of coal, assume that the coal mine needs 0.1 ton of steel is used. So these two are now interrelated. How do I find out how much I can produce? Well, if we want to produce 400 tons of steel and 300 tons of coal, then we can sort of start drawing this out, and we need, if I want to produce 400 tons of coal, or steel so I can sell it, and 300 tons of coal so I can sell it, I have to remember that it takes coal to make steel. So really, I have to make 300 plus 200 tons of coal, because I'm going to use 200 to make the steel. But to do that, I'm going to have to also make more steel than 400 because of 30, and I get this sort of looping kinds of structure. So as those interact, we have to remember this is now a coupled system. So they're related. You can't just look at that and say what the solution is going to be. So we have to look at it slightly differently. Let's look at the total output of the steel plant as 0.1 times the amount that goes into coal plus 400. And then we can look at how much goes into coal as 0.5 times the amount that goes into steel plus 300. And now you can sort of see we have two equations. And we can put those two equations in standard augmented matrix form, try and solve it, and I get a value for XS and XC. So straightforward. If we go a little bit farther and now we start trying to expand this to 3 items, it becomes a little bit more complicated. So I can talk about how much steel goes into power, power goes into coal, coal goes into power, power goes into steel. All of these are related. So you can put these together and now build a distribution of how outputs are related and build a set of equations for these. And now we can ask a slightly different question, not just how much is moving between them, but our question becomes, can we find the price of steel, coal, and power such that the cost is to each industry balances with its income? That is, can we find the equilibrium price? And as I said, this is really just an example of a much larger class of equilibrium problems. So if we let the price of steel, coal, and electricity be given by P sub with each of the different letters, and we start with the idea that expenditures equals incomes, we're going to get 3 equations. The production of steel, the price of steel depends on the price of steel, coal, and electricity. Coal depends on the other 3, and electricity depends on the other 2. And so we're just taking our output from and relating it to the idea of equilibrium. So we build this matrix. We can try and put it into standard form. And we now have a problem. Because if I actually go to do this matrix and solve it, it's going to be singular. In fact, so here I put in the matrix in the MATLAB, and I just got the SVD decomposition, and you can sort of see the results. And you can see that here, S has 2 singular values that are greater than 0 and 1 that's equal to 0. This is rank 2. And this is classic of equilibrium problems. We'll come back to that. So is there a unique solution? No. So the more interesting question is for us to ask, what is the space of solutions? So to get the space of solutions, I'm going to take 0 from my right-hand side. I'm going to multiply it by U inverse, and I'm going to take only the parts of our singular value matrix that are not equal to 0. So in this case, I'm just going to use the notation D from 1 to R, where R is the rank. And we already just said the rank is 2. I didn't compute it, but I could have. Element Y is divided by S, where S is the diagonal of our singular value matrix. And I'm going to fill the rest of it with zeros. And I'm going to multiply that, and that'll give me X. And when I get done, X is 0. I can't solve it in a simple least squares solution. So what can I do? Associated with the 0 eigenvalue, or the smallest eigenvalue. And in this case, that is just taking the right column of V, the third column of V. The first two are valid singular values. The last one is 0. So I just take the third column of V, and that gives me an answer. And I'm going to normalize it just to give me a nice normalized answer. And to interpret that, I can then say I'm going to have, if I let P of electricity equals 1, because I normalized, then we have the price of steel will be 0.64 and the price of coal will be 0.74. That's just normalizing that data out. And you see 0.64, 0.73, and 1, just from normalizing the data. And if we were to set the price to be 100, then these prices would, of course, be multiplied by 100. And if you think about it as a price, it, of course, makes sense. There's no unique solution because all we did was talk about production, of how much of this material moves in or out. So there's no unique solution. It's going to depend on the currency. Am I doing this with US dollars or yen or rubies or whatever else we want, right? Clearly I changed dollars to yen and the numbers change, but the ratios don't, which is what we end up getting out of the solution. As another example of something that's going to be an equilibrium problem, let's think about a traffic flow problem. So here I have a complicated traffic circle. People can go in one and out one, so it's a roundabout or a circle connecting 5 roads. The counter, as the traffic moves, the question is, how much traffic can I expect to see? Well, one of the reasons this is an equilibrium problem is, at every node I can have some number of people coming in, some number of people leaving, and if they don't leave, they have to continue around the circle. And then the next one, some people can leave, some people enter. But if I don't have an equilibrium, then what's going to happen is there will people be stuck in the circle. They'll be growing in the circle. So there's a bunch of variables that are related, but these variables are going to be constrained. But we can talk about how much traffic will be on each segment and try and find that solution. So if I do that, I can look at these flows as in and out and a free variable, and then I can write down, in this case, with 5 nodes, 5 equations. I can put that in an augmented matrix form. I could try and solve it, and I will, so here's my nice matrix. It's, in fact, a pretty structured matrix. When I go to solve that, I can put in some right-hand side, and I will find out, unfortunately, that it doesn't work. Because again, even though the matrix here looked almost like an identity matrix, right? It's almost upper triangular with this one last value down here, the matrix turns out to not be solvable. It's singular. It has a single, 1, 0 singular value. And again, you can almost guess why, because I didn't tell you what the units of those things were. The car, it could be number of cars, thousands of cars, hundreds of thousands of cars. There's not a unique solution. And again, the way we solve that, if we do it with respect to SVD, is I can take the solution, I can get the rightmost column out of V, and that will give me the relative ratios of what those elements will be. Okay, so as we wind this down, just a sort of bit of review, SVD's relations to eigenvalues. So if A is equal to our singular value decomposition U W V transpose, and I let the x of j be the ith column of V transpose, then we can actually see why x of j is an eigenvalue of A transpose A. And that's how we're solving this. So the eigenvalue we get for this equilibrium problem for the last column gives us directly our solution to the equilibrium problem. So the elements of W also turn out to be the square root of the eigenvalues, and the columns of V are the eigenvectors of A transpose A, and that's what we wanted for this robust least squares fitting. So one of the nice things about SVD then is I can take SVD and I can just take elements of V to get my eigenvectors of A transpose A. So if you think back to your FACE experiments for your second programming assignment, you could have gotten the eigenvectors from A transpose A or AA transpose from this solution. As I mentioned, the SVD is the best approximation in terms of the Frobenius norm. It's probably worth mentioning what that is. So the Frobenius norm can actually be computed from SVD because of their relationship. The Frobenius norm is defined as the sum of the squares of each element of the matrix. So if I just take each element of my matrix, I square it and sum them all up, that's called the Frobenius norm. And it turns out I can estimate that by just looking at the sum of the squares of the singular values of the matrix. It's not estimate, it is the value. So if I do some modifications to a matrix, I can ask what happens by looking at this Frobenius norm. Last application, which we're not going to spend much time on because we've already done this, is SVD is directly related to PCA. So for PCA, you recall, we take our original axes, we have some data points, we then find the first principal component of those and the second principal component of those. And the nice thing is, if I want to do this for a set of data, and I stick this data and shove it in through SVD, I'm going to get those axes. First we subtract out the mean like we did for our faces, and then the columns of VK are the principal components. And the value of WI, or singular values, give us the importance of these. These are weights that go together, and very, very much related to what we did for eigenfaces. And many implementations of eigenfaces and PCA and those kinds of things actually use SVD instead of the approach we took because it turned out to be a little bit more numerically stable. Last thing I want to relate SVD to is the condition number. In next class, we'll actually be looking at numeric stability and condition number, so I just want to sort of define it. If I look at my SVD, I have two orthogonal matrices, U and V, so these are easily invertible, and these tell me everything is going to be, when I multiply by them, I can do it easily. So if there's any instability in my matrix, it's going to turn out to be in the singular values. The singular values, if we think of them as sorted from smallest to largest, I can define what's called the condition number of the matrix as the ratio of the largest singular vector value divided by the small singular value. If it's singular, C would be infinite, so I can just chop it off and I can look at it, and if the matrix is ill-conditioned if that number is too large. And we'll talk more about that next chapter, but I wanted to sort of show it to you here. So there's a bunch of terms from this chapter. Make sure you know them. I didn't cover all of them in the video, so because we'd already done PCA, I skipped a bunch of the stuff related to quadratic forms and how you can look in PCA in terms of quadratics. But make sure you know all these terms, again, for the final. For some of the applications, there's actually a couple of other things I looked at. There's some books on Golub and Van Loon's book on matrix computation. There's actually another nice book called The Matrix that gets into this, and then some papers that I cited in terms of